When we talk about nothing in our everyday lives, we usually mean an empty space. But in cosmology, nothing is much more complex. It's not just the absence of something. In the realm of the cosmos, nothing is not empty at all. It is teeming with possibilities. To grasp nothing in cosmological terms, we need to think beyond our ordinary thoughts. We have to delve into the world of quantum physics. Here, nothing is a place where particles constantly pop in and out of existence. It's a sea of energy that we can't see or touch, but it's there, buzzing with activity. The concept of nothing is key to understanding how our universe began. It's the very fabric from which everything emerges. This idea challenges our common sense. As we explore the birth of the universe, keep in mind this new idea of nothing. The Big Bang Theory is our best explanation for how the universe began. It says that about 13.8 billion years ago, everything started from a single point. This point was incredibly hot and dense. It was even smaller than an atom. Then, in an instant, it rapidly expanded. This expansion is what we call the Big Bang. But what was there before the Big Bang? This is where our idea of nothing comes in. Scientists believe that before the Big Bang, there was no space and no time. It's hard to imagine, but as we understand it, there was literally nothing. Then, from this nothing, our entire universe came into being. The Big Bang Theory explains many things we see in the universe today. It explains the cosmic microwave background radiation. This is leftover heat from the early universe. The journey from nothing to everything is still a mystery in many ways. Quantum fluctuations are tiny changes in energy that happen at the smallest scales. They are a key part of quantum mechanics. These fluctuations are happening all the time, even in what we think of as empty space. They're so small that we can't see them directly, but they have a big impact on the universe. In the context of the universe's creation, quantum fluctuations played a crucial role. Scientists believe that these tiny energy changes were the seeds of all the structures in the universe. As the universe expanded after the Big Bang, these fluctuations grew. They became the foundation for galaxies, stars, and planets. The idea of quantum fluctuations challenges our normal way of thinking. It suggests that even in nothingness, there is constant activity. Particles are popping in and out of existence in the void of space. It happens so fast that we can't see it directly, but the effects are real and measurable. Stephen Hawking was a brilliant physicist who made groundbreaking contributions to our understanding of the universe. He worked on black holes and the Big Bang. Hawking explained that the universe came from nothing. Time itself began with the Big Bang. There was no time before that. His no-boundary proposal suggested that the universe has no edge. Hawking radiation showed that black holes aren't entirely black. Part 5. The concept of vacuum energy. Vacuum energy is a strange and fascinating concept in physics. It's the energy that's present in space, even when that space is completely empty of matter. This energy comes from quantum fluctuations. It's a key part of our modern understanding of the universe. The idea of vacuum energy challenges our everyday notion of empty. In quantum physics, empty space is never truly empty. It's filled with virtual particles that pop in and out of existence. These particles create a kind of background energy that permeates all of space. Vacuum energy may have played a crucial role in the early universe. Some scientists think it provided the push for cosmic inflation. This was a period of rapid expansion right after the Big Bang. Vacuum energy could explain why this inflation happened. Understanding vacuum energy better could help us unravel this mystery. Part 6. String theory and multiple dimensions. String theory is a complex idea that tries to explain all the forces in the universe. It says that the fundamental building blocks of reality are tiny vibrating strings. These strings are so small that we can't see them. They vibrate in different ways to make up all the particles we know. One of the most amazing things about string theory is that it requires extra dimensions. Our everyday world has 3 spatial dimensions, along with time. But string theory says there could be 10 or 11 dimensions in total. These extra dimensions could be so small and curled up that we can't detect them. The idea of extra dimensions helps explain how nothing could become something. In these extra dimensions, there might be more room for quantum fluctuations to happen. This could provide the energy needed to start the universe. Part 7. The Multiverse Hypothesis. The Multiverse Hypothesis is an idea that stretches the limits of our understanding. It suggests that our universe might not be the only universe. Instead, There could be many universes, perhaps an infinite number. Each of these universes could have different physical laws and constants. This idea comes from several areas of physics. Quantum mechanics suggests that multiple possible outcomes can exist simultaneously. Inflation theory proposes that the universe expanded incredibly fast early on. Some versions of this theory predict that this process creates many universes. The multiverse concept helps explain some puzzling things about our universe. For example, the values of some physical constants seem fine-tuned for life. In a multiverse, this could be explained by the idea that we simply happen to exist in a universe where these values allow for life. Part 8. Notable experiments in cosmology. Cosmology relies on both theory and observation. The discovery of the cosmic microwave background radiation provided strong support for the Big Bang theory. The Hubble Space Telescope has provided incredible views of distant galaxies. LIGO detected gravitational waves, opening a new way to observe the universe. Part 9. Unanswered questions in universe formation. Despite all we've learned about the universe, many questions remain unanswered. One big mystery is the nature of dark matter and dark energy. These make up most of the universe, but we don't know what they are. Another puzzle is matter-antimatter asymmetry. The Big Bang should have produced equal amounts of matter and antimatter, but our universe is made almost entirely of matter. We don't know why this imbalance exists. Part 10. The role of dark matter and dark energy. Dark matter and dark energy are two of the most mysterious components of our universe. Dark matter is invisible stuff that we can't see directly. We know it's there because of its gravitational effects on visible matter. It plays a crucial role in holding galaxies together. It also helped to shape structure in the early universe. Dark energy is even stranger. It's a force that's accelerating the expansion of the universe. We don't know what it is, but it makes up about 68% of the universe. Dark energy might be a property of space itself. Understanding it is crucial for knowing the ultimate fate of the universe. These dark components challenge our understanding of the universe's creation. In the early universe, dark matter was crucial. It created gravitational wells where ordinary matter could clump together to form galaxies. Part 11. Conclusion. Our ongoing quest to understand the cosmos. Our journey from nothing to the universe we see today is an ongoing story. We've made incredible progress in understanding the cosmos, but every answer brings new questions. Ideas like the Big Bang theory, quantum fluctuations, and the multiverse have expanded our view of reality. Yet, mysteries remain. Dark matter, dark energy, and the nature of the vacuum continue to puzzle us. The origin of the universe itself is still not fully understood. These unknowns drive scientific inquiry forward. They inspire new experiments and push the boundaries of our theories. As we continue to explore, we must be open to new ideas. The history of cosmology shows that our view of the universe can change dramatically. What seems impossible today might be common knowledge tomorrow. The important thing is that we keep asking questions, keep observing, and keep testing our ideas against reality.